it's time to start the second part of this workshop of today. Thanks again to be here because coffee time is important and also networking. But again, we have to move on. And please, my apologies because at the beginning I did not present Federico, that is there from ETA, and is doing a very interesting job today, which is a sort of art mixed with notes. So it's a way to mix together these two things and try to provide you a graphical visualization of what we are doing here today. So you are invited for sure to go there, see what he's doing, and also to provide the feedback, because for sure everything can be done in a different way, depending also from your point of view. Now we move to topic 2, which is focusing on the conversion side from biomass to product. And it's a pleasure to invite here Christopher Kick from the Fraunhofer Institute in Germany. And the topic is about transforming biomass, cutting-edge conversion technologies for clean biofuel and beyond. Christopher?
Welcome to the TCR2 pilot plant of this project, combining phytoremediation and advanced biorefinery at TRL5. Before the conversion trial starts, we conduct a comprehensive systems check, pumps, valves and sensors, to ensure uninterrupted biomass feed and process safety. Throughout the trial, all key parameters, temperature, pressure, and gas flow, are monitored in real time via Grafana dashboards. Here we see how set points from the control panel are directly communicated to the plant actuators, closing the loop for fully automated control. The condensate fraction is drained and visually inspected for clarity and absence of particulates, key indicators of oil quality. The biochar, a byproduct of catalytic pyrolysis, is evaluated for particle size distribution and color, critical for its downstream applications. In our mobile lab, we perform gravimetric separation to quantify oil versus water yield from the condensate. A high-speed centrifuge is used to remove remaining water from the oil phase, enhancing its purity for further upgrade to sustainable biofuels. The Synol unit converts TCR syngas to liquid hydrocarbons via a microchannel gas-to-liquid process, enabling drop-in fuel production. Collected samples are labeled, secured in vials, and transported under controlled conditions to the analytical laboratory. In the lab, we perform elemental and hydrocarbon composition analyses to validate product quality and process performance.
Yeah, thank you very much for to be here today. the big question is, where are the heavy metals? And this is still a riddle, but and the secret, but I will answer this in my talk in the end. So, but to begin with, my name is Christopher Kick, and I work for Fraunhofer Umsicht in Sulzbach-Rosenberg. And we really did the technical part, so we tried to convert all the biomass we got from our partners to biofuels. Oh, sorry. So the content of my talk is about, first of all, I want to show you about Fraunhofer and the organization, so what we're doing, to give you, to visualize for you what kind of technical centers we have and where all these conversation trials were done. And then I directly hop into the phytoclimate project and tell you about the specific objectives we have had, all the goals and the tasks we did, our activities and results, and in the end, I'll give a conclusion and show some highlights. So could we really achieve to convert all this biomass, and what was the quality of the products we achieved? But first of all, as I said, I want to say something about Fraunhofer Umsicht. So we are the biggest applied research institute in Europe. We have about 30,000 employees and 76 institutes, mainly in Germany, but also throughout the world. And our funding is done such that the majority of the funding we get, we have to provide for ourselves, basically from industry, but also from public sector. And 30% comes from the German state. We have about 6,000 customers worldwide, and we have 8 affiliates throughout the world. And basically, we create spin-offs, and we live from protection of IP. So we're patenting our ideas, basically. And this is where Fraunhofer is. I said it's application-orientated, so we're not doing basic research, but we're right before industrial scale. This is where we are, and this is where we feel comfortable. And as I said, we have 76 institutes, and Fraunhofer Umsicht is the 7th largest. We have about 600 employees, and we have 2 locations, and I'm staying here in Sulzbach-Rosenberg in Bavaria, in the southern part of Germany. We have 4 focus topics: circular economy, carbon management, green hydrogen, and local energy systems, and everything which is done within phytoclimate was done within the focused topic of carbon management. Just to give you an idea how it looks like in our technical center, where we also did all the conversion trials, this is a visualization, and we have different kind of conversion technologies in there to convert biomass, but not also biomass. So this one, the pyrolysis reactor here, which has a capacity of 2 kilograms per hour, was used for phytoclimate, but we also can have another one which is used for plastic pyrolysis. And then coming more to the front, we have all these downstream applications where we distill our products we get from the conversion or do the hydrotreatment. And also we are constantly testing new advanced thermochemical conversion technologies, like here up front, a pyrolysis gasification reactor, where we, after producing biochar, we gasify it to produce even more gas, then eventually going for gas to liquid processes. So I showed you this in a lab scale, in a technical center, but we do this also in a bigger scale, and this is now an example of a biorefinery which a scale of already 500 kilograms per hour, which converts sewage sludge to really biofuels. And this is also one of our technical centers we have. And now coming to the phytoclimate project and our contribution really within that project. You have seen this picture, but I'm showing this here again because it really illustrates what we did. And we took the contaminations from the soil via plants, produced biomass, and then tried to use innovative biorefinery technology to convert this to to biofuels, in the end for road and transport. But on the other side, the question was, well, if we now have the heavy metals within the plants, where do they finally go? For our approach here, it was such that we hoped that it will stay in the biochar, and then this biochar could be a substitution for fossil coke in the copper smelting industry. And this is what I'm going to show you also later on. So as I said, we were really for the development of this biorefinery and for the production of these biofuels. The overall objective was to test the biofuels produced with the standards which are out there for marine fuels, but also for diesel and gasoline. And to reach these overall objectives, we had several specific tasks. First of all, we had to build up this biorefinery. We did that in the first period of the project. And then we evaluated our products. And finally, with all the knowledge gained from the conversion trials, we built up a mass and energy balance for the total biorefinery as a baseline for the business for the business models, which would be developed later on then. Well, before I directly hop into the biorefinery we used within Phytoclimate, I wanted to say something again, that what we used is basically one option which is possible to convert biomass, but there are lots of them, and some of them already were said. And I think it's important to know that every biomass is unique, and you have to take into account for each biomass which conversion route you want to go, and also it very depends on your targeted product. For us, this was a very elegant way to use pyrolysis because we wanted to have the char and the heavy metals in it. We wanted to produce gas to finally produce a liquid energy carrier, and also we wanted to have bio oil, which should be upgraded to marine fuels. This is basically the way we did it. So we had in the beginning a pyrolysis unit where we basically put in the pre-treated biomass from all our partners. So we heated it up and then without oxygen. And what happens is that we produce biochar and pyrolysis vapors. And these pyrolysis vapors are then led to a second reactor, which is filled up with very hot biochar. And these vapors, they have to flow over this biochar. And then there are second reactions. And this is basically where the magic happens and where the product quality of the pyrolysis intermediates are again upgraded. So what in the end, we're producing high quality biochar. We're producing a syngas, which is very rich in hydrogen, up to 40%. And we're producing a bio oil, which is thermally stable, means it can be upgraded later on in classical and standard refineries. And we're producing also an aqueous phase, and this aqueous phase has some organics in it, and we have to purify it. But not only do we want to purify it, we want also to use it as a source for hydrogen, because it was also said today, if you want to use the gas in a gas to liquid process, you always have a lack of hydrogen. And you need an additional source. In our aqueous phase, this was exactly our additional source for doing this. And in the end, we wanted to produce biofuels according to these norms, and finally, we compared them. Well, to reach all these goals I just told you, we divided our work package in different tasks, and I will now lead you through these tasks in order that you have an understanding of how we reached our goals. First of all, I told you we had to plan and design and build this biorefinery, and this is basically the core unit here, the TCR2. So you can put in 2 kilograms per hour of feedstocks, but it's only the core. So all the periphery had to be developed and to be built up. Basically a gas purification unit to purify the gas we produce, a gas compressor to compress it before we bring it to the gas to liquid plant, because it works under pressure. But also we had to build up an electro-oxidation test stand to purify the water and provide the additional hydrogen. And then all the rest, meaning the distillation unit and all the sensors and all what is needed. So this was all done in the first period of the project, and it was done successfully. And once we had reached this, we could then start doing our trials. And well, beginning this, you have to think about, okay, how am I going to convert all this biomass, and what kind of parameters do I want to monitor, and what kind of results do I want to get? So we used the first harvest. So we got 3 harvests from each partner. And we used the first harvest to do basically parameter optimization. So we had a look on what biomass, what kind of conversion temperature would be the best, and not only temperature, but also residual time within the reactor. This was all assessed in the first harvest. And then the result was that we know now for each biomass which is the best conversion parameter. And then for the second and third harvest, we tried to verify this and produce more of the biofuels, so we eventually could then compare it with the standard norms. Coming to the first part, basically to the conversion of the biomass to the intermediates. So to speak, to the aqueous phase, to the gas, to the oil, and to the biocoke. And as I said, we tested all the biomass we got from our partners. This can be seen here. So we tested rapeseed, quinoa, herbaceous mix, jerusalem, artichoke, and sorghum. And I said for each feedstock, we had 3 temperatures ranging from 550 to 750 degrees. And then what this graph shows you, the black one is the char, the gray, the dark grayish is the aqueous phase, then in green the oil phase, and the light gray the gas, is that the higher the conversion temperature, so if you go up from 500 to 750 degree, the higher the gas amount of gases, and the lower the amount of all the other products. This is true for all of the tested feedstocks. However, the absolute values are different. So for example, if your targeted product is the oil, I would say you should take the herbaceous mix purely from the amount of oil you're producing. At 550 degree, you're producing 11% compared to if you use sorghum, where you only produce 4%. So, but this really depends on what you're targeting. If you come to the energy balances, which is basically the mass balance times the higher heating value of the individual product, the picture is the same. So the higher the conversion temperature, the higher energy, the higher the amount of energy from the feedstock can be found in the gas phase, and the less for all the other products. Not only have we tested feedstocks, pelletized feedstocks, and directly put them into our conversion technology, but we also got oily seeds from rapeseeds, because we also wanted to test, if you're taking rapeseed, if the heavy metals are not just in the plant but also in the seeds. And this is why we basically harvested the seeds, and then what we did is we extracted it, so we pressed the seeds, and we got a press cake, and we got vegetable oil. And then we tried to transestericate this vegetable oil to biodiesel and see if this is applicable according to the standards for biodiesel. Well, this can be seen here. So this is the tranesterification experiment yielding finally our biodiesel. But then in this case, this was rapeseed from Serbia, and they had very specific heavy metal contamination. But when I tried to compare this with the norm for biodiesel, those heavy metals could not be found in the norm. So apparently, this would have to have been aligned in the future. So, but the overall amount of heavy metals within the biodiesel from this rapeseed was very, very low. So I'm pretty sure we would have not succeeded any thresholds if there would have been one. So, however, there are other limits in this norm. And for all the values here in green, we are within the norm, and for all the values here in red, we're over the threshold of this parameter. And if there are some red, I am very confident that this is only true due to the laboratory setup we used, and if we would have optimized this, I'm pretty sure that we can also reach the other parameters. For example, here the water content is still too high. Well, then you have to dry it. I mean, or for example, the alkaline earth metals are here still too high, but you could wash it. So there are lots of options to do this and to finally reach the standard. So I consider this as a first trial, but I'm pretty optimistic that if we optimize this a little bit, this standard can be easily met. So coming to the TCR oil, it was meant that after distillation, it should meet the specifications for marine fuels. And let's see if this could be reached. So this is the distillation experiment. So we used the biocrude we got from the TCR process and then distilled it. And distilling it yields two fractions, a distillate and the residual. The residual is this, what is left after the experiment is done. And it looks like, in our case, it looks like really solid charcoal. And the goal here was, here a KPI was given that we reach 70% of distillate and only 30% of residual is left over. And for all the tested oil fractions from Lithuania, herbaceous mix, Jerusalem artichoke, but also from Spain, sorghum, we could reach between 70 and 80% of distillate. So this goal was obviously reached. And now we had to compare this with marine fuels. And I was surprised, but there are lots of different types of marine fuels. And they are classified in this norm according to 3 categories. And the lightest one is marine gas oils. So it's basically a blend of different distillates from the distillation of fossil fuels. And then there is marine diesel oil. As the name already applies, it looks more like diesel and it has a higher energy content. It looks also already a little bit darker. And this now is already a blend between distillates and residuals, so the leftovers after the distillation. And now here, the last one is the heavy stuff. This is this intermediate fuel oils. Probably our phytoclimate container ship also drives with this one right now. Yeah. So this is lots of residual and a little bit of distillate. This is really sick stuff, and sometimes without heating it, it's solid. So it has to be heated to even be burned in a combustion. And now we try to basically compare our distillates with this fuel classes. I don't expect you to read everything here in this table, but I wanted to give you the keynotes here. So those 3 rows basically show three tested distillates from 3 different from 3 different feedstocks. And here the lines show different parameters. And if we compare it to the marine gas oils, so the lightest fraction, then the most important things here is the ones in red, because this is the parameters which are still not met. All the others are met. But if I have a look on these parameters, and then I see, okay, the density is not met, the water content is too high, and there are some fine particles left in the oil, which are just too much. But for this, I can take measures. I can reduce the water amount by drying or stuff like this. I can filter the particles, and if I reduce the water content, probably also the density would come down. So also here, I'm pretty optimistic that we're not far away from from reaching all these parameters within the specifications, I mean, we just started, and but we're already very, very close to reaching this goal. And then, if you compare it to the other two classes, it's basically the same picture. The density is too high, and the water content is too high. And there are two different parameters, new other parameters here in this norm, the flash point and the ignition quality. So how easily is it to ignite? Yeah. And these are also parameters which I'm pretty sure if you optimize this, then we're very close to reaching also this goals. Coming to the TCR water, I said there is also water produced doing this pyrolysis, and this water has to be purified. And it should also be a source for hydrogen for the gas-to-liquid plant, which converts basically the rest of the gas into liquid energy carriers. And here also we build up a test stand, seen here on the right side. And then basically what this technology does is it uses electricity, and you place electrodes in your aqueous phase, and then you use a very specific electrode and not hydrolyzing water, doing the electrolysis of water, producing oxygen. No, you reduce the organics on the anode, and this is shown here, starting from about 7 grams per liter. During the process, we could reduce this almost to 100 milligrams per liter, and now this would be then able to be released to a sewage treatment plant. And on the other side, while doing this, we produced enough hydrogen on the cathode, which then could be also a feedstock for the gas-to-liquid process. And this is what I'm going to show you now, the gas-to-liquid process. And here I have to say, well, in the beginning, we tried to use the Fischer-Tropsch process, but we encountered several challenges for mainly some gas components are very poisoning to the catalyst used in this process, and they have to be below parts per billion. And this is something which is very challenging in a technical way, and it's for sure not economically feasible if you want to have decentralized plants like this. So in the end, we decided to go for another process called a Sunol process, which is a more robust process. It uses a cheap ion catalyst. So even if this catalyst is deactivated, it can be easily and cheap replaced. However, there is a price, and the price is that you're not producing biodiesel or gasoline, you're only producing precursors, so some oxygenated liquid hydrocarbons. And this is what I want to show you. Here again, an overview of what we have tried to test and what we finally end up. So the Sunol process, and it works at the temperature range of about 190 to 200 degrees, and it also operates on 25 bar. Well, this is our test stand where we tested this. On the red, you can see the inlet for the different gas components, and then the gas mixing unit, the compressor, and after the compressor, it is directly led into the reactor with the catalyst, and then here is where the reaction happens, and finally you should end up with a liquid product which you then can analyze. And this on the right side shows you basically the catalyst preparation. As I said, it was an ion catalyst. So right now, trials are still going on, by the way. Right now we have already 4 trials done, started with a process temperature of 190 degrees up to 220 degrees at 25 bars of pressure, and with a different production techniques of the catalyst. So at some point, the catalyst was not activated, while for the other trials it was activated, just to see how this what implications this has on the final product. Well, and in our first round, we got a big mixture of various hydrocarbons. But we only want to focus on 2-hexanol as our targeted product. And this is what we want to optimize. And so we did all the following tests basically trying to increase this product. And this graph shows you basically that this was something we could reach. So we started from a very low amount, and after the fourth trial, testing all these different parameters in temperature changing, but also in the activation of the catalyst, we could at least triple the amount of this liquid, yeah. And as I said, it's still going on, but we're very optimistic that we even can reach further efficiency of that process. Coming to the last part, to the biocoke, and the question, and hopefully the answer, where the heavy metals are. So, I'm sorry, but I cannot really answer this question sufficiently because it's not clear. Literature tells you that most of the heavy metals should end up in the biocoke. And for most of the heavy metals, we basically see this. So this graphic is the same. Black shows the biochar, and this light gray shows the gas phase, and this green shows the oil phase. And this 100% tells you basically whatever heavy metal amount was found in the feedstock, how it is now found how it is now distributed within the products. So, for example, if you had 100% cadmium in your feedstock, now 16% after conversion at 550 degrees, 16% is in the char, 28% here would be in the oil found, and 56% would be in the gas phase. But I have to say, this might be not the reality, because it is very hard. So first of all, the amount of heavy metals in the products are very low. So your failure could be very high doing the analysis. And also, if you want to extract the heavy metals from the biocoke, you could also do, there are lots of ways to do a failure, and you could maybe not extract all of it. And then this value here, which tells you how much is in the gas phase, is basically the calculation of those two, yeah? So, and if you don't extract all the heavy metals in the biocoke, you make a mistake, and then you would assume that you find the majority of cadmium in the gas phase, but maybe it's there, but you just didn't get it out while analyzing it. So it's still unclear. We're working on this. But I mean, for the majority, it says that chromium, copper, nickel, and also zinc is with the majority could be found in the biocoke. And this is exactly where we want to have it, because we want to bring this biocoke in the copper smelting industry to be a replacement for fossil coke. And if we can trap all the heavy metals in the biocoke, then we also have a possibility to recover these heavy metals then finally in this process. Well, and if it works, if it could be a substitution in the copper smelting industry, this is shown here, and the result is much clearer, and I can easily answer this with a yes, because if you see, the most important thing, the most important test is basically this coke reactivity index, and it basically tells you how fast it burns and how much energy is released. And if you compare this on the left, on this figure on the left side here with standard coke, which is used, standard fossil coke, which is used right now, you see that for all the tested biocokes, this coke reactivity index is much higher. So all of the biocoke work for this application, which is great. It's a really great result, because now we would have a very good application for our biocoke. Well, and in the end, I think the scene is set. The scene is set to bring this approach from lab to industrial scale. Basically, from this picture here to this picture here. We gained really an understanding of what kind of feedstock and what kind of process parameters would yield specific intermediates and what the quality of the those intermediates are. We also get promising results in regards of the quality of these intermediates and then comparing this to these standard norms which are out there. And then we verified that the biocoke could be a substitution for fossil coke in the copper smelting industry. And as a highlight that all the heavy metals which are in this biocoke, not all of it, but the majority, could be recovered in the copper smelting industry. And then finally, we set the scene by developing this mass and energy balances now for the whole biorefinery to give somebody the chance to really build up a business model and scale this approach up. So I am very, very optimistic that this approach can work, and I think if we all work together and join forces, then we can bring this to the next level. Well, I said this for the technical part. Now the question is, what about the economical, the ecological, or the legal part? And this is what you will hear from my colleagues in the next presentation. Thank you very much.
Thank you very much for this nice presentation, and we open the floor for questions. So, do we have some questions? Isabella?
Very good question, and there is also not one answer for this. It's very specific to the biomass availability and also the infrastructure and the biofuels needed in this region. So it's very diverse, and I cannot answer this with just one answer. Yeah.
Do we have more questions? So, no? Just one on the back. Professor Sanei, please.
That was a great presentation. How about mercury? Is mercury ending up in biochar or how is it fractionated?
Well, mercury is by itself very volatile, so probably it doesn't end up in the biochar with increasing temperature. So you either find it in the oil, or because if you condense the vapors, probably mercury will also be there. And if it doesn't, if it's not in the oil, finally, it will be in the gas phase. So you have to make sure that whatever comes out there on heavy metals, this is true for all volatile metals, they are securely trapped in a purification of the stream.
Yeah, just to follow up on that, coal industry, they use activated carbon to capture mercury from flue gas.
Mm-hmm.
Maybe you could use that in the biochar to also capture the mercury from the volatile matter.
Yeah, thank you for this idea. We also talked about this because it makes sense. Biochar is already there, and if we could load it with even more heavy metals and then bring it to the copper smelting industry, this would be a plus for the approach.
Okay, if there are no more questions, I would have the last question. So, I'm very interested about the last part that you mentioned about the biorefinery concept. So, I understood from the presentation that closing the mass balances of contaminants is quite challenging. I guess both for the scale of the project, the scale of the pilot units, probably the error of measurements of some equipment used to quantify the metals. But I wanted to ask you how far we are to propose a model of biorefinery coupling the process that you think are the best one for the biomass investigated. I mean, how far we are for the market development of this solution.
I mean, the question goes in the same direction as
just to complete, I've seen that you showed at a certain point, if I understood well, the 2-hexanol that could be one of the product, and this is not a fuel. This is also an alcohol, so it could have also other roles. So in the optic of biorefinery, I think this is quite important to be mentioned as high added value. So just to know about it.
Yeah. Maybe to start from the second question, what we tried in this project was really basically trying to convert everything. So we used every technical possibility to convert all the streams we've gained from the pyrolysis. And this is not something you would do if you build a specific biorefinery for a specific feedstock, but because you're constrained with various things, mainly economic constraints. And so you really would have to focus on a specific product and on a specific biorefinery concept. So this was basically the general biorefinery. And then now for a specific feedstock, you would cross some lines in this biorefinery and really condense it down to a working biorefinery, really only focusing on your targeted product. And to your first question, because it directly links, we have done this scenarios for various regions, and this is something I guess it will be shown in the next presentation. So we are close to basically giving an answer to how this could look like in a scaled-up version.
Thank you very much, clear. Oh, okay, so I would go on with the next speaker because we are just a bit late. So we are to the final topic of today, that is called Towards Sustainable Solution, examining LCA, economic viability and regulatory framework. So we have some speakers from this session. So I would like to invite the first speaker, that is Karolina Petela, and then Thomas Sibilla from the Silesian University of Technology in Poland. So please. And then please, you can call your other speaker.
Good morning, buongiorno. My name is Karolina Petela, and it is mine and my project colleagues' pleasure to have the presentation on the steps towards the sustainability assessment of our phytoclimate technology. And thank you, Christopher, for the introduction already. Okay. So indeed, having now the core background of our technology regarding phytoremediation, the biorefinery concept, TCR process, it is time now to describe and answer the question regarding the relation of our technology with the surroundings, with the external surroundings. So by that I mean environmental effect analysis, but also legal aspects and economic viability. So let me now start with our part. that is LCA. So me and Tomasz Simla work as postdocs at Silesian University of Technology in Poland, and it was our team's opportunity to perform LCA, so life cycle assessment of this whole chain of phytoclimate. And let me now start the bottom part. Yeah. Oops, no. Yes, let me now start with the first bomb. So we have a lot. We have 4 pilot sites with soils with different contaminants where the different plants are grown, which will become different biomass that will become a feedstock, different feedstocks. And then we have biorefinery with a list of products. All that should be covered by LCA. Different scenarios should be described and defined, different boundaries for this kind of analysis, and it is already, well, overwhelming before you start. So now let me give the floor to Tomek to put the challenge of explaining these things. I guess this one.
So welcome, and as Karolina mentioned, the most important task of our team in work package 4 was conducting the life cycle assessment, which is a methodology to assess the impacts of a given process or product in the entire life cycle. And in general, I think conducting any kind of life cycle assessment is a challenging task. But in the case of phytoclimate, it was especially challenging because, as Karolina mentioned, we have various functions of our entire process. We have the phytoremediation, where our goal is to clean the soil as soon as possible to restore it to agricultural quality. But we also have the biomass processing, where our task is to produce biofuels that could then replace fossil fuels, as we can see here, from the traditional supply systems, which results in reduction of CO2 emissions, for example. So already one of the first challenges was to draft the boundaries of the system and define the functional unit, because one of the first steps of life cycle assessment is to define something called the functional unit. What function exactly our system is supposed to fulfill? And we have this soil cleaning, biofuel processing, so it was a challenging task. Eventually, we decided for practical reasons that we're going to go for phytoremediation of 1 hectare of contaminated land for 1 year, which in theory should give us some biomass that we then process in the biorefinery. We initially split the analysis into 2 parts, one for the phytoremediation and then for the biomass processing. And then for the combined process, we assumed a biorefinery unit that has a processing capacity of 3.9 thousand tons of dry biomass per year. And then the next challenging task was to collect the data, the inventory data for all the sub-processes that are included in the system boundaries. So first of all, we have the phytoremediation, where we use some fuel, some energy at the, for the agricultural processes. We use some fertilizers, some water. So for that, we asked our pilot site partners to provide it with the data. In the later stages of the project, we also use some literature data to simulate maybe a more large-scale approach with more optimized use of resources. And then we have the biorefinery part, which again consists of several processes which Christopher explained half an hour ago. We have the TCR process, we have the electrooxidation, the gas to liquid. So the next challenge was to collect all the energy and material inputs for these processes. For this part, we also needed to perform some mathematical simulations or do some literature research to find the missing information. And the last part inside this system boundary is the avoided use of coke, avoided use of other fossil fuels, because in our approach we assume that we produce these biofuels, biocoke, which means that we avoid a use of an equivalent amount of fossil fuels, which in the end results in avoided emissions, for example, avoided CO2 emissions, which in theory could lead to a negative CO2 result, negative CO2 emission results of the entire process, which means that we have avoided some greenhouse gas effect due to our approach. And we analyzed several variants, 3 variants for from the perspective of phytoremediations, 3 types of plants, sorghum, rapeseed, and herbaceous mix, which also were supposed to be grown on different type of contaminated soils. And for the biorefinery, we analyzed 3 variants of the configuration: the full biorefinery with the synol process to convert gas into liquid, and 2 simplified variants where we do not process the gas, we just combust it on site to produce either just heat or heat and electric energy. So in total we have 3 times 3, that's 9 variants that we analyzed. And on the next slide you can see a big table with a lot of numbers. Of course, it's not time and place to talk in details about these numbers, but I'm showing this table here because, as you can see, a lot of these numbers are in green. And that means that they are negative, which means that we have avoided some environmental burdens due to our approach, mainly for 2 reasons. 1, because we avoid the use of fossil fuels, and 2, we remove the contaminants from the soil. So it's like negative emissions to the soil. I would like to point out especially this part, the category called human toxicity, and thanks to the removal of contaminants, as you can see, most of the numbers for most of the variants, we have these 9 variants, are green. We have avoided pollution in the environment. Also, what's important is this category here, climate change. And as you can see, for all the variants, we have avoided CO2 emissions, mainly thanks to replacement of fossil fuels. We also did the calculations specifically for the CO2 emission savings according to the European Union's Renewable Energy Directive. And as you can see, for all 9 variants that we analyzed, the values are close to 100% of CO2 savings. So how is that possible? Well, since we are growing biomass on degraded land, we can account for a bonus of CO2, like avoided CO2 emissions, which is related to the improvement of quality of the soil, the enrichment of the carbon content of the soil. And since our processing emissions are not very large, in the end we get about 0, close to 0 emissions in theory, which results in about 100% emission savings according to the methodology. So the most important conclusion here is that if we manage to properly optimize the biorefinery concept from the energy point of view, because the use of energy is the most important contributor to the environmental impact of the biorefinery. So if we reuse the heat streams in the refinery, maybe if we combust the gas, produce electricity, which we then also use in the refinery, we can achieve very positive environmental scores. And now I would like to ask Karolina for the social acceptance part.
Okay, so let us say that with these results, so with these LCA results, with these numbers, we have the first grades for our project, for our technology, which is important for the internal judgment, for the assessment stuff, but also important in terms of social acceptance concept. According to this concept, there is a triangle where social political acceptance, market acceptance, and community acceptance are defined. So actually, the parts regarding the market acceptance and the legal acceptance will be covered with a bigger presentation afterwards by Lucas and Marco. But we also managed during the project to check the community approach, so check the ground, what is the people's perception, and we chose small community members living close by to the pilot sites, and thanks to pilot site leaders, we managed to perform the questionnaires and check what is their perception and potential approach towards implementation of that kind of technology in their neighborhood. And actually, the first results of the questionnaires were quite predictable. The main barriers were revealed, we found out that lack of understanding, lack of involvement of people, lack of visible profits might be the arguments against innovative implementation of innovative technology, and these are the aspects that should be addressed later on by introducing a social acceptance toolkit. Actually, our project did quite well, from my perspective, regarding the promotion, and with that raising the awareness about this kind of innovative technologies and raising understanding of phytoremediation, biofuel productions, and so on. So we have actually here just there are listed the channels through which we reached people's attention. There were also kind of workshops that people were able to attend, or stakeholders were able to attend, regarding community acceptance, socio-political and market acceptance. There was also a second round of post-survey when people were already provided with some kind of information regarding the project with help of infographics and video about the project, and also again it led to a simple conclusion that if people are provided with knowledge, with introduction, even to the most innovative technologies, they are more eager, more willing to support that kind of technology implementation. Of course, there is space for enhancement, for improvement, but that is what we found out till now. And with that simple conclusions, I will now give the floor for the next corners of the social acceptance triangle, and I will give the floor to Lucas.
Okay, thank you very much, Carolina. My name is Lukas Brunbauer. I work for ETS Förderberatung. It's an Austrian consulting company, and we have the honor also to coordinate this project. My colleague Markus Ortner is the project leader. So we were investigating the economic feasibility of this whole process and to examine the business potential. So from contaminated land to valuable products, is that possible? Does that pay off? And the answer is, depends what you compare it to, I would say. And we will find out more about this. We already heard today several times that this process works. It is functional and effective. We can extract the heavy metals, or they can be, or the contaminants can be stabilized. The biomass can be converted. We know that, and the biochar is a very valuable product, especially for the metallurgical industry, and it has a high potential of CO2 savings, as we learned from Thomas before. So I think throughout this project we have achieved an upgrade in the TRL level from 5 to 6 and 7. So it is ready for the proof of concept. Marcel will explain some about the what we compare phytoremediation to.
Hello, good morning. This is Marcel from Lithuania, which is a consultancy company regarding to soil, contaminated soils and remediation. So in this part on work package 5, regarding to the business case model, we wanted to compare the phytoremediation with other techniques or remediation techniques. And we kind of, first of all, had to put some context, and we worked in a heavy metal contaminated soil, which the contamination was in a shallow way and only in soils, not in groundwater. So regarding to heavy metals, and as Marcus said before, which is very challenging due to they do not volatile, they do not degrade, and etc. So we approach that in just 4 remediation techniques. There is more remediation techniques, but they do not apply to heavy metals. Okay, so first of all is the condemn. It's the excavation with machinery and etc. and to transport to a landfill, and it's generating a hole somewhere and filling a hole into another way. So it's the less sustainable technique. So it should be avoidable in all cases. Second one is the containment. It's to perform a little landfill in your very place or in your site. Then you kind of accumulate your contaminated soil, and you have to perform a little landfill with some impermeable layers and etc. in order to contain all the contamination and avoid it to leachate or get to the subterranean groundwater and etc. You have to be sure that the containment is performed properly. And there is a couple more. No, the other way. Okay, then for the heavy metals, you can try to stabilize the heavy metals. You have to perform some preliminary tests because sometimes it's easy to stabilize some metals, but some other it's difficult, or some other, while you can stabilize some metals, then some other ones do not get stabilized. And here, what we want to do is you do not remove the contamination, but you are sure that the contamination remains stable and that it do not leachate and do not generate leachates, and it does not get to the groundwater and some other places. And you have to monitor it all as well. And obviously the phytoremediation, which you have been very well taught during this meeting, is the 4th case that has been studied in the Work Package 5. So Lucas, the floor again. Thank you very much.
Thank you very much, Marçal. And now the question is, so what are the figures? What are the numbers? Here we calculated we did several scenarios, and we tried to figure out how much does it cost to remediate or to treat a hectare land. And we compare it to the other types of treatment, I would say, and we learn that with dig and dump, a hectare of land, contaminated land, costs about 2 million euros to treat, to excavate and replace it, or relocate it somewhere else. Stabilization, 600,000, and containment, 200,000. And with the phytoclimate approach, depending on many variables, we can reach a cost between 60 to 230,000 euros per hectare. So, according to this, it is a very feasible way, economically feasible way to treat soil. But what are the main cost drivers? Why is it not, why does it still cost, actually? And the cost drivers are that this phytoremediation process needs a lot of monitoring and analysis. This is not just agricultural work, as Shigemantas pointed out. It is more than that. And it is a staff intensive process. We need a lot of human resource, and that makes it expensive. And unfortunately, the products that come out of it have a rather low market value. So from the 230,000, this is already the result after using or selling all the products. But that does not change it in a very large scale, I would say. And of course, as in many technical things, the economy does matter. The economy of scale applies here as well. So we assume that if this process is upscaled, if we don't only have one TCR 500, but if we have 6, we can of course change the whole business model. And on the other side, what are the strengths of this approach? That the biochar is a very valuable product in metallurgy, for example. The CO2 reduction capacity, as has been pointed out several times. There is also a potential for gate fee, building a model with receiving contaminated biomass and process it in the TCR in combination with biomass from phytoremediation. The process can be optimized and the land value increase. And here, just a very small side note, and maybe this question is in your head. What is the value of a land? We discussed this several times. It's very difficult to say. There is no actual model that can tell you the real value other than the price. And lastly, when is phytoclimate a good solution? When dig and dump is or stabilization are the option. Phytoremediation is a more feasible or economically better way to do. When there is renewable fuel shortage, so maybe this will happen sometime in the future. When there is lots of marginal land or unused land, we could use that to produce biomass and process it and receive the products. And when there is a need for biochar. And lastly, when there is time for doing phytoremediation. I asked Marcel yesterday how much they do a lot of remediation projects, what is the percentage they do, and I was very shocked to find out that only 2% of their business is phytoremediation. So I really think there is a lot of potential to do more of that. What are we looking for? I am hoping for a real-world demonstration of this approach. Yes, there is a couple of scenarios lined up, I would say. We're thinking about, or there are talks about applications in Germany. We have ideas for applying it in Serbia. Exolum might have a case where this could be applied. We are hoping for public incentives to support this approach and partnerships, carbon markets. And lastly, the legal frameworks for supporting this approach are essential, and that's my turn to hand over to my colleague and friend Marco.
So good afternoon from my side. Before I start officially with my presentation, I would like to say big thanks to the ETA Florence team for warm hospitality and the organization of this final event of the phytoclimate. So grazie mille per tutto. So today we'll hear also something about legal part of this project. Believe it or not, but there's a lot of legal issues in the whole value chain of this project. Let me just shortly explain what I, together with my colleagues, are doing, what are the tasks. So very shortly, we firstly started with the word potential. So potential regulatory issues and legal obstacles throughout the entire value chain. After the analysis, we then found definite barriers, but also opportunities. The best legal practices are actually the fruits of the comparative analysis. So in our project, there are 4 mandatory legal frameworks that we had to examine. So Spanish, Argentinian, Serbian, Lithuanian. However, since this is innovative approach, this is something niche, something new, it also involves some other countries for our analysis and also to be up to date. Finally, our final task is to provide recommendations for decision makers. And when I said we, who we are, so Bernard van Hoesden is the main supervisor of the work package 6. He's also director of the Hasselt University. My colleague Jonas Vorter is a work package leader, and Paola Galbiati Silviera and I are doing the research. How we do it? So this is our analytical approach, or as we call it, stepwise approach we developed for the phytoclimate purposes. So from the first phase, so from selection of plants for phytoremediation, and I may say in the first phase we have very controversial categories that are more under the legal limitation than the legal support. For instance, alien species, GMOs, new genomic techniques. Then we are dealing with the next phase, which is implementation of phytoremediation. We have here fertilizer, pesticides, and irrigation. Those are all vital agricultural practices. Finally, in the harvesting phase, we already heard about extraction, about phytoextraction mechanism, and we are dealing with 3 very unpopular categories, with waste, with byproducts, and also with the step when waste stops being waste, so when reach end of waste criteria. Those are my parts. My colleague Paola are dealing with biomass conversion. So we have sustainability criteria, both as an opportunity and barrier, financial support, more limitation, advanced biofuels distribution, certification schemes, and end-use advanced biofuels, incentive schemes. But to provide the recommendations, which are the fruit of 4 wonderful years of work in the amazing group of colleagues from various fields of environmental science, I can say that we are recommending here regarding the first categories, so regarding alien invasive species and GMOs. For alien invasive species, or just alien species, they're not unique opinion regarding that. Should they be really applied or not? So our suggestion, if you must, then maybe it should be the best to use the evidence-based approach, international criteria, and also scientific progress. Regarding genetically modified organism, or the symbol of negativity, as I can say freely, we need revision of GMOs legislation at the EU level in order to provide possibility of using genetically modified organism that can possibly enhance the phytoremediation, and that especially tackles the new genomic techniques So around the world, countries are already developing separately, also regulating the new genomic techniques from the GMOs framework. And EU is way behind that. It's not in the game of the big players. Regarding, I mentioned 3 vital agricultural practices. So phytoremediation is similar to agriculture activity, but can it be defined as such or not? It will depend on national legislations. Somewhere yes, somewhere no. But what we suggest to definitely update the common agricultural policy with wording transformation capacity of phytoremediation to transform contaminated land into arable land. Regarding waste, byproducts, and end-of-waste criteria, the biggest problem here that one company can find is that there is no traceability. We don't know anything about the quantity. We don't know the final destination. Each country is dealing with that completely individually. There is no EU-wide harmonization criteria neither regarding byproducts, neither regarding end-of-waste criteria. For certain things, yes, like scrap metals, yes, but for this, no. So what can be helpful for commercialization is basically establishment of registers, okay, and also chronological archives. Finally, companies also find themselves in difficulty how to do a self-assessment. Is it waste? Is it not waste? Has been recovered enough or not? And we are suggesting to establish at the EU level guidance with the chemical legislation, so that connects the products that are coming after the harvested phase of phytoremediation to be aligned with chemicals legislation, which is even more stringent than waste legislation. And that inspiration could be drawn from Flemish self-assessment. Next, regarding biofuels recommendations, those are recommendations from my colleague Paula. So definitely implementation of internationally recognized biofuels sustainability frameworks that has to be aligned with the climate neutrality commitments. Second, to modify the Annex 9 of the REDS that refers to advanced biofuels with innovative and less mature technology, such as TCR, for instance. And this one is highly connected to the last one. So in this annex, it should be remove the limitation in which purpose advanced biofuels can be used. Right now we have only for aviation sector, we have also different sectors. So we propose to, if must impose some kind of limitation, then it can be on technology, but not regarding the sector. Finally, to amend sustainability criteria under the Renewable Energy Directive 3 to account the benefits that are coming from nature-based solutions, so like phytoremediation, and especially regarding soil quality. For the conclusion, it's win-win solution, definitely. It also contributes to the 3 Rio Conventions that are dealing with land degradation neutrality. It's amazing approach, it's innovative approach, but we need to discover its full potential. We are still learning. There is also a strong gap in knowledge about phytoremediation. How it can be closed. One example is our project, workshops, conferences, events like this to spread the words about it. It opens green job opportunities against those who are talking that the green approaches are not business oriented. We heard from my colleagues, from Lucas and from Carolina that yes, it is. We have also trends of increasing demand of biofuels in the future. But still, it's important how we will produce. It's not the same if we are for instance, using arable land for biofuels production. But before that, I can say that what is sometimes most important is to overcome the legal barriers to make it really possible. And if you would like to know how, don't hesitate. We from Hugh Hasselt are dealing with that. So from my side, it was a real honor and pleasure to work with you. I hope that we will continue in the future. Thank you so much, and all the best. If you have also any kind of question, I'm here.
Thank you very much to the all speakers that participated to the last round of presentation. It has been really interesting to see both the economic, environmental, and regulatory aspect all together that used the result produced from the first two topics and try to apply them to create a sort of real outcomes that could be used for the next projects, because the scale must be scaled up for sure. So do we have some questions for the speakers? Please.
Yes, this is a very important aspect of the carbon balance, to know exactly how much the agricultural activities on the degraded soils contribute to the change of carbon balance. And the conclusion from this study is that this requires some really precise, more precise measurements that maybe have been planned in this project. So from this particular project, of course, there were some measurements of the carbon content in the soil before and after the trials, but the problem is that the uncertainty of the results is so high that we can't really tell with certainty in which direction even the carbon content went. So it's something that definitely should be taken care more in the future approaches. However, from the legal point of view, in the Renewable Energy Directive, it explicitly states if we grow biomass on land that was degraded, that was not used previously, that is polluted and so on, we can get a bonus of 29 grams of CO2 per megajoule, regardless whether the carbon content actually grows or not. So these are these two aspects, the legal aspects of getting the bonus and the actual change of carbon content, which needs to be measured precisely, which in this project we had a lot of uncertainty.
Maybe an additional comment, it's not only the total carbon that is relevant, but it's also the stability of the carbon. There are different fractions, some are labile and could be degraded, but some fractions could be stabilized, especially in chemical forms strongly bound to clay particles. So I think this is perhaps going beyond what could be done in a project like this, but if there would be a future project looking specifically on the carbon sequestration potential, I think it's important to look at different carbon fractions and not just measure the total carbon content. This is only part of the story of assessing potential sequestration in the soil.
Yes, I totally agree, because some of the carbon can get released to the atmosphere pretty soon, and we shouldn't account for it in the life cycle assessment.
Thank you. Do we have more questions? Okay, so just a quick question from my side to probably that is a mix between the interpretation of the regulatory framework and the outcomes from this project. So in the last year, I have the opportunity to work to support the preparation of the update of the Annex 9 of the Renewable Energy Directive that has been mentioned before, which is a list of feedstock that divided in two parts, Part A and Part B, that are, especially Part A is the list of feedstock that could be used to produce advanced biofuels. So the problem is that doing the hypothesis that this contaminated biomass could fit some one of these categories in a certain way. The challenge now is to demonstrate to the policymakers if we are going towards a bigger production that we are not doing frauds. This is the main challenge from my side because today we have probably some scandals about using cooking oil for advanced biofuel and other feedstocks. So if there's someone, maybe the last presenter about that have an idea on how to try to overcome this potential problem which could limit a lot the scale up of this kind of biomass. Please, please.
Well, this part is of my colleague Paula. I cannot share everything here, so I don't have that kind of permission, but I really think that the main problem, as you said, about frauds, is that the policy decision are not always sure if it's really contaminated land, because it's right, am I right, it's about it. So if you're going to, I don't know, plant the energy crops on the land that is not contaminated. So there's also another problem there regarding two definitions. It's highly connected. So we have severely degraded land. So if it's severely, phytoremediation cannot be applied then, because phytoremediation can be applied only if we have moderate kind of contamination, not something, yeah, very highly contaminated. That's one thing. Then there is another level. That second definition is abandoned land, but both definitions are not saying anything about contaminated land. That's also an issue. Why is that? It's also connected that there is no soil legislation on supranational level, where it should be definition of contaminated land. So I think the annex, so your question, it's also connected to the problem of those two definitions. I think, from my side, I think the Commission should really clarify what does it means, both of them. Because as it is right now, I think it gives us some sort of leeway how someone can really do frauds or greenwashing or whatever, you know. So yeah, that would be my point of view. Thank you.
Thank you. Okay, so we are going to close this event. It's the time to start the last part of this event, and it's a pleasure to conclude inviting on the floor Professor Ahmed Zanei, which is director of the Lithospheric Organic Carbon Laboratory from Aarhus University in Denmark. So, Professor Zanei, it's a pleasure to have you here, and in the time that is coming, it's a pleasure to say that Professor Zanei is an expert on biochar analysis. In particular, he contributed a lot in the last year as regards the development of the carbon removal certification framework, trying to address the carbon stability within biochar. So his expertise will for sure help all of you to understand which will be the main outcomes and recommendation beyond the result of this project. So please, Professor, thank you.
Thank you so much, Marco, Stefano. Thank you very much. And thank you. It's a great honor and pleasure to be here. As Marco mentioned, I'm here in Florence for 8 months of sabbatical, 7 months of sabbatical research with Professor Chiaramonti. Not a bad city to be on sabbatical, so really greatly enjoying it. And you know, today, for instance, was a clear example of why I'm here. I was a student sitting there and listening to great work you are doing, which is quite different from what I do, but because I'm a geologist and I work on carbon cycle, geological carbon cycle. Anybody geologist here in this room? Oh, wow, we got 2. That's great. So I don't feel lonely here. So yeah, I work on organic geochemistry and petrology. So we geologists, we have a very kind of a long-term perspective of things. You know, I often found, I'm not saying it's good or bad, sometimes it's bad. You know, people think we are not relevant. You know, we were thinking millions of years. But that also gives us this advantage of putting things on a broader perspective. And why I'm saying that is, you know, I'm listening to the way you do your research and what you are trying to do for the environment. That's exactly how Earth does things. You know, that's a real natural process of Earth. By taking advantage of the carbon cycle, biospheric carbon cycle, and you know, remediate contamination through the carbon cycle and using thermochemical process to produce energy while storing some of the carbon in the permanent or long-term form that would stay you know, in the environment through different applications. I think that's exactly how nature stores carbon. For instance, I give you an example. I'm not sure if it is in the plan for your research. I heard a lot of biocokes, use of biochar to apply for metallurgical application. But one other application that I've become quite interested is use of biochar in cement industry and in concretes and building constructions. Because that's also a way of storing carbon. And of course, if the carbon is originated from contaminated sites, you could also store some of the contaminations in a very stable form in you know, construction in a solid form that would stay there for thousands of years. So these are something that perhaps you know, you could look into that in future. But I don't want to talk too much here. But I'll you know, my geologist friends, they know that we always look at rocks, the sedimentary archives, you know, the layers of rocks, to see what happened in the geological past. We know, for instance, there has been bad time during the Earth's history. We call them extinction periods. Those extinction periods are usually, when you go look at the markers, you would see there was always Earth has reclaimed the bad time during the Earth's history. And usually, the way Earth did it was through carbon cycle, by storing carbon in the geological form, so then it could remediate the bad effect of atmospheric effect at the time. So, you know, what I usually say, I say, you know, through the work that you are doing, maybe in the millions of years in future, when people can see the geological records of Anthropocene or humankind, they could see that, well, at some point, these species, they really messed up with the whole things. But somehow they figured it out, and you could see by the way they reversed the carbon cycle, and now adding more carbon into the barrier or geological processes. So that's a little bit more kind of a broader geological perspective that I usually share with colleagues. But I really enjoyed this session. Well done for organizing this, and thank you for inviting me. I'm not here to give you a lecture. I was merely a student and listening to the great work you've done. Particularly in the first half of my research career, I worked on contaminants, and particularly on mercury and also partly on lead and arsenic, and seeing how you're using natural processes and then thermochemical process to bring these contaminations into something perhaps safe, and along the way you're using the carbon cycle to work for the environment. I think that's really encouraging. So thank you very much, and I think it's been a really great and successful day. Thank you.
Thank you.
So we would like to conclude this event with the final words of Markus, the coordinator of the project. And then lunch.
Yes, this was the key word, lunch. I think all of us, we are already hungry and looking forward to have some lunch, so I'm somehow between this. I will make it short. Thank you very much, first of all, to every one of you, all participants. I made some notes before that I do not forget anyone here, so thank you very much for all participants and guests coming here to this beautiful venue here in Florence to listen to our project, to be also active in the discussions. Thank you very much for that. Then I also would like to thank ETA Florence, this Stefano and the entire team behind the organized these rooms, the whole event, everything which you didn't see it, but this was a lot of work in the past weeks, so thank you very much for the ETA. Then, of course, a special thanks goes to Marco Buffi, the one and only moderator, for guiding us so smoothly through this event. Then, of course, also a big thanks to our two keynote speakers, Isabella and Markus Buschenreiter. And, of course, also a big thank you to our students, as he used these words, Hamed Semeh, for the closing statement and for this wider view on these aspects. I really liked it. Thank you very much for being with us. Then a very big thanks goes to our project photographers, Guillermo and Christian. So, yes, these guys are here. This is Christian, you can see it coming in, and Guillermo is... You will see him later, okay? Again. Yes, and of course, also a big thanks goes to Federico, our graphical recorder. You noticed him, of course, so he was here on the right-hand side. From your view, he was painting everything what we were talking, and you can watch then afterwards during the lunch outside this beautiful painting. Thank you very much for this. And last but not least, and finally, thanks to my whole project team. Without your hard work and spirit, nothing of this would have been possible. Thank you very much. Yes, and with that, I would like to close this final event. And before we go to lunch, I would like to invite you to come downstairs. I think also the lunch is downstairs for a group photo. Okay?
just